Pick up any rock off the ground. Turn it over in your hand. Look at the surface. Most rocks give you nothing. Gray, uniform, unremarkable. But some carry surface marks that are visible without any equipment. Chemistry written in color and texture that points directly to what's inside or nearby. Gold, silver, copper, and gemstones don't hide perfectly. They leave traces. Learning to read those traces on the surface of common rock is a field skill that most people never develop because nobody tells them what to look for. This is what to look for. The most common valuable surface sign on rocks is also the most ignored because it looks like damage. Orange, rust brown, or deep red staining on the surface of otherwise gray or beige rock. Informative, that color is iron oxide. Specifically, it's what happens when iron sulfide minerals oxidize after years of exposure to air and water. Pyrite, arsenopyrite, and pyrohite all turn into iron hydroxides and iron oxides when weathering hits them. The result on the rock surface is that rust orange color that most people step over without a second look. Explanation: why does this matter for gold? Because iron sulfides are the most common host minerals for gold in the geological record. Gold deposits in rock are almost always associated with hydrothermal systems. The same conditions that produce the pyrite produce the gold. When the pyrite oxidizes and stains the surface orange, the gold it was associated with stays behind. Iron dissolves and weathers away. Gold doesn't. Curious, so the orange staining on the surface is pointing to where the sulfides were, and where the sulfides were, gold has a statistically significant chance of still being present in the fresh rock below. In mining, this oxidized surface layer over a sulfide deposit has a name. It's called a gossan. Geologists chase gossans specifically because they mark mineralized zones that are worth drilling into. You don't need a drill to start. You need to stop walking past orange rock. The second surface sign is structural rather than chemical, a white vein cutting across darker host rock. Informative, quartz veins form when silica-rich hydrothermal fluids move through fractures in rock under pressure and temperature. As the fluid cools, silica precipitates out as quartz, filling the fracture. The result is a white or pale gray stripe cutting across the darker host rock in a pattern that is completely different from normal rock layering. Explanation: the reason quartz veins matter for gold is that the same hydrothermal fluids that deposited the quartz also transported gold, silver, and other metals in solution. As the fluid cooled, metals precipitated alongside the quartz, concentrating at the edges of the vein where the hot fluid met the cooler host rock. That zone, the contact between the white quartz and the host rock on either side, is where the highest concentration of metals tends to sit. Informative, on the surface of a hand sample, a quartz vein alone tells you a hydrothermal system was active. Combined with iron staining, the probability that the system was also mineralized with gold increases significantly. The combination of white quartz and rust orange iron staining on the same rock surface is one of the most reliable field indicators available. Curious, if you find a rock in a geologically active region that shows both, it deserves more than a glance. Some rocks carry their metal content on the surface in a way that removes all ambiguity. Green, bright saturated green in patches on an otherwise gray or brown rock surface. That color is malachite, a copper carbonate mineral that forms on the surface of copper-bearing rock as the primary copper sulfide minerals below oxidize. Malachite is chemically stable at the surface and holds its color for thousands of years. Malachite on a rock surface is a direct indicator of copper sulfide mineralization below. The green color appears where the copper-bearing zone intersects the weathered surface. The intensity and distribution of the green can tell you roughly how concentrated the copper is and how deep the fresh mineralization extends. Copper deposits are frequently associated with gold, either in the same ore body or in adjacent zones, because the same hydrothermal systems that concentrate copper also concentrate gold in many geological settings. Beyond gold association, copper itself has significant value. A rock with heavy malachite staining on its surface is showing you a copper deposit. How large that deposit is depends on the geology of the area, but the surface indicator is unambiguous. Malachite is never accidental. It requires a copper sulfide source to form from. If the surface shows it, that source exists. Sometimes what a rock is telling you shows up not in color, but in weight. A rock that feels wrong for its size, heavier than you expect, before you even know what you're holding. This happens when the rock contains dense minerals. Gold has a density of 19.3 grams per cubic centimeter. Galena, the primary ore of silver and lead, has a density of 7.6. Barite reaches 4.5. Compare those numbers to quartz at 2.65 or granite at around 2.7, and you start to understand why a mineralized rock feels different in the hand. A fist-sized piece of galena weighs almost 3 times what a fist-sized piece of granite weighs. That difference is immediately apparent when you pick it up. Galena is recognizable on the surface by more than weight. It has a bright silver-gray metallic luster that is distinctive, a high reflectivity, and a tendency to break along clean, flat surfaces called cleavage planes that create cube-like faces. Fresh galena on a rock surface looks almost too perfect to be natural, with its mirror-bright cubic faces. Galena is the most common ore of silver and frequently occurs alongside gold in polymetallic deposits. A rock with visible galena on its surface in a geologically mineralized area is a field specimen that warrants collecting and proper identification. Pyrite gets dismissed as fool's gold, and for good reason, since it has almost no value on its own. But dismissing pyrite without understanding what it's pointing to is a mistake. Pyrite on the surface of a rock looks like clusters of perfect golden cubes or irregular metallic masses with a brassy yellow color and a high reflective shine. Unlike gold, pyrite's color changes slightly with the angle of light because its flat crystal faces act like tiny mirrors. Gold looks the same color from every angle. The geological significance of pyrite is that it forms under the same hydrothermal conditions that produce gold deposits. In many ore bodies, the gold is not visible because it's either too fine to see with the naked eye or it's locked inside the pyrite crystal structure itself as submicroscopic inclusions. Some of the largest gold mines in the world, the Carlin-type deposits in Nevada, mine rock that contains no visible gold at all. The gold is distributed in microscopic particles inside Arsenian pyrite grains. When you see pyrite on a rock surface, you're not seeing fool's gold. You're seeing the chemical signature of a system that could have produced real gold nearby. The question is always the context. Pyrite in a granite intrusion in a productive gold district means something different than pyrite in a sedimentary rock nowhere near any known mineralization. Location doesn't make pyrite gold, it makes it worth paying attention to. Vugs are small open cavities in rock, sometimes lined with crystals, sometimes empty. They look like tiny holes or pockets on the surface of a specimen. They form when minerals dissolve out of the rock after the rock formed, leaving voids, or when gas bubbles were trapped in cooling lava and the walls of those bubbles were later coated with mineral-rich fluids. The key thing about vugs is what they were coated with. Quartz is the most common vug lining in hydrothermal systems. Calcite is the second. But in mineralized systems, vugs can be lined with gold, silver, native copper, or gemstone quality crystals. The gold in some of the most visually spectacular specimens ever found grew inside vugs in quartz veins, forming what collectors call specimen gold or wire gold. A rock with multiple small vugs visible on its surface, particularly if those vugs show crystal linings, and the rock also has iron staining or quartz veins, is a specimen from an actively mineralized hydrothermal system. The cavities are where the last fluids passed through and deposited what they were carrying. What they were carrying is what matters. Silicification is a surface change that's easy to miss because it doesn't announce itself with color, it announces itself with texture and hardness. When hydrothermal silica-rich fluids pass through rock, they deposit silica in the pore spaces and along grain boundaries, making the rock harder and denser. The result is a rock that resists weathering better than the surrounding rock, often standing as ridges or resistant outcrops, while softer rock around it erodes away. On the hand sample level, silicified rock has a harder, more glassy or chert-like appearance than unaltered rock of the same type. Sedimentary rock that has been silicified often looks like flint or jasper with a smooth, slightly waxy fracture surface. Silicification in the context of hydrothermal systems is significant because the same silica-saturated fluids that silicified the rock also carried metals. Zones of intense silicification in productive gold districts are prospecting targets because they represent areas where large volumes of metal-bearing fluid moved through the rock. This applies to surface prospecting too. A rock that seems unusually hard, that has a chert or flint-like surface when broken fresh, in an area with any other indicators of hydrothermal activity, is worth noting. Breccia texture on a rock surface looks like a mosaic, angular fragments of one rock type cemented together by a different material filling the spaces between them. Breccia forms when rock is shattered by explosive geological events, by the rapid release of pressurized fluid, by fault movement, or by volcanic activity, and the fragments are subsequently cemented by minerals precipitating from circulating fluids. The cement between the fragments in mineralized breccia can include gold, silver, copper sulfides, or other valuable minerals. The high surface area created by all those angular fragments in contact with the cementing fluid made breccia zones extremely efficient at capturing metals from passing hydrothermal fluids. Some of the richest gold ores ever mined were in breccia pipe deposits, where a column of brecciated rock cut through granite and the cement between the fragments was heavily mineralized. On the surface of a hand sample, breccia texture is unmistakable. Angular pieces of darker rock in a lighter cement, or the reverse. If the cement shows iron staining, metallic mineral specks, or any malachite or azurite, that breccia is telling you something about what passed through it. Color zoning in rock, where the rock surface shows distinct patches of purple, pink, cream, or green that don't correspond to different rock types, is a sign of hydrothermal alteration. Different alteration styles produce different colors. Potassic alteration turns rock pink to red from potassium feldspar and biotite. Argillic alteration produces white to cream from clay minerals replacing feldspar. Propylitic alteration gives a green color from chlorite and epidote. Phyllic alteration produces a pale gray to off-white from cerussite. These color changes occur because hot mineralized fluids passing through rock chemically react with the minerals they contact, replacing some minerals with others. The type and distribution of alteration visible on the surface tells a geologist which part of a hydrothermal system they're looking at and how close they might be to the central mineralized zone. In classic porphyry copper and gold systems, the alteration types occur in concentric zones around the central intrusion. Knowing which alteration type you're looking at tells you which direction the mineralization is and roughly how close you are. For field prospectors without laboratory tools, the practical application is simpler. A rock that shows unusual color patches that aren't just surface staining, that seem to penetrate the fabric of the rock itself, is a rock that has been through something chemically significant. That something is worth investigating in the context of the local geology. Some of the most overlooked valuable rock surfaces are the ones that have already been partially opened by natural weathering. A fresh break along an existing fracture can reveal what the rock has been hiding on every surface that hasn't seen air in millions of years. When you find a rock with a naturally occurring fracture surface, one that looks older than a fresh break, look at that surface under different light angles. Metallic mineral grains that are invisible on the weathered exterior often show up clearly on the fracture surface. Galena on a fracture surface shows its characteristic cubic cleavage. Pyrite shows its brassy cubic faces. The principle is that the weathered exterior of a rock is chemically altered. Minerals that were metallic and reflective when the rock was fresh have been oxidized, converted to oxides and carbonates, and lost their original luster. A fresh fracture surface cuts through material that hasn't been altered and shows the original mineralogy more clearly. This is why prospectors crack rocks. A rock that shows surface iron staining on the exterior can reveal on a fresh break the pyrite that produced that staining, and sometimes, alongside the pyrite, gold that is completely invisible from the outside. Gold visible to the naked eye on a rock surface is rare enough that most people who find it don't recognize it for a few seconds. The color is wrong compared to what jewelry looks like. Gold in rock is almost always associated with quartz and frequently has a duller appearance than polished gold because the surface has been through whatever the rock surface has been through. It can look orange-yellow, brassy yellow, or in some specimens where it's very fine, it can look like a pale yellow shimmer rather than a distinct mass. The test that confirms it immediately without any equipment is the scratch test. Press something harder than gold against it. Almost any rock surface works, and gold deforms rather than scratching away. Gold is soft enough that a fingernail can mark it under pressure. Pyrite scratches away to a powder. Gold flattens. The locations on the rock surface where gold most commonly appears when visible are along quartz vein contacts, inside vugs in quartz, on fracture surfaces in or near quartz veins, and sometimes as fine threads or wire-like formations in cracks. These formations, wire gold and leaf gold, are among the most visually distinctive mineral specimens and some of the most valuable by gram for the collector market. A 1-gram specimen of wire gold in quartz can sell for many times the raw gold value because of its rarity as a formation. The practical point is this. When you're looking at rock in quartz, especially quartz with iron staining nearby, look at the contact zones between the quartz and the host rock. Look inside any cavities. Look on any fracture surfaces that cut through the quartz. Gold, when it's there and visible, tends to sit in exactly those positions. A rock's weight relative to its apparent volume is one of the fastest pre-screening tools available with zero equipment. This takes practice to calibrate, but the principle is straightforward. Quartz and most silicate rocks have similar densities in the range of 2.5 to 2.8 grams per cubic centimeter. A rock that is substantially heavier than a comparable piece of quartz-rich rock of the same size is carrying minerals with higher density. Gold at 19.3, galena at 7.6, barite at 4.5, cassiterite at 7.0, and magnetite at 5.2 all produce a noticeably different feel in the hand than quartz or granite. Cassiterite is the primary ore of tin and appears as dark brown to black heavy grains or masses in rock. It frequently occurs in quartz veins associated with granitic intrusions and is another high-density surface indicator worth knowing. A dark brown to black, heavy mass in quartz with a submetallic luster that is significantly denser than the surrounding rock is often cassiterite. The practical point is this. When you're looking at quartz in rock, especially quartz with iron staining nearby, look at the contact zones between the quartz and the host rock. Look inside any cavities. Look on any fracture surfaces that cut through the quartz. Gold, when it's there and visible, tends to sit in exactly those positions. Turquoise appears as bright blue to blue-green patches on certain types of rock, specifically in arid or semi-arid regions where copper-bearing rock has been exposed to long-term weathering. Turquoise is a copper-aluminum phosphate that forms in the near-surface zone above copper deposits when phosphate-bearing water ground reacts with copper-bearing rock. The bright color is diagnostic. No other common surface mineral produces that specific combination of blue-green in the copper deposit context. The rocks that host turquoise are typically intensely fractured and altered, often showing both iron staining from pyrite oxidation and the blue-green copper carbonate staining of malachite and azurite alongside the turquoise. The turquoise itself is not necessarily an indicator of gold. It is a direct value in its own right as a gemstone and collector mineral. High-quality turquoise from certain producing regions sells for several $100s per gram. In the American Southwest, turquoise occurs in association with copper deposits in Arizona, New Mexico, Nevada, and Colorado. Recognizing the bright blue-green of turquoise on a rock surface in those regions is a field skill with direct financial implications. Matrix turquoise, where the turquoise fills fractures in the host rock and creates a veined pattern against the brown or black matrix, is particularly valued in the lapidary market. Every sign described here is available to you on the surface of a rock without laboratory equipment, without expensive instruments, and without formal training. Iron staining, white quartz veins, green malachite or blue azurite patches, unusual weight, metallic mineral specks, breccia texture with mineral cement, color alteration zones, visible gold at quartz contacts, vugs with crystal linings, silicified texture in otherwise softer rock. None of these are rare in geological terms. They appear on rocks in creek beds, road cuts, riverbanks, desert washes, mountain slopes, and excavated construction sites. The difference between finding them and not finding them is almost entirely whether you're looking for them. The geological processes that produce these surface signs operated over millions of years and left physical evidence at every scale, from microscopic mineral inclusions to visible staining on the surface you can see from arm's length. That evidence doesn't disappear because nobody is looking at it. The rocks have already done the work of concentrating what they contain and marking the surface to show where it is. The only remaining step is learning to read what the surface is already showing.